Welcome back, Virtual Precalculus. This is the last section in Chapter 13 that we're going to work on, and it's about normal distributions. Normal distributions are a way to model many different kinds of natural phenomena. It's also known as the bell curve, which I'm sure you guys have heard of, and it can also be called a Gaussian distribution, named after the famous German brilliant mathematician Carl Friedrich Gauss. Like I said, it models lots of different natural phenomena, especially in situations where there are a large number of objects. Examples include the kinetic energy of a large number of molecules for an object in thermal equilibrium, the IQ of a large population of people, the height of a large population, and maybe the test scores of a large population, like the SAT. Like the name bell curve implies, it is shaped like a bell. It is symmetric about the mean, and it can be completely specified mathematically by two parameters: the mean, for which we use the Greek letter mu, and the standard deviation, for which we use the Greek letter lowercase sigma. It is a probability density distribution. So it's going to tell us how likely it is that various events are going to take place. By changing the mean, we're going to be able to shift this thing left and right, a translation horizontally. And by changing the standard deviation, we're going to be able to stretch it or compress it. When we stretch it vertically, we compress it horizontally. When we compress it vertically, we stretch it horizontally. We're not going to really focus too much on the translations in the way that we've done them before, though. Alright, this is what the normal distribution looks like. Please don't run away and cry. I know it's scary, but I want to show you how to use it in at least an example here so that you see that it's just a big hunk of junk that you can handle. You just plug things in and crank them out as usual. So, the probability of whatever parameter you're talking about, whether it's temperature or height or IQ, the probability that that thing has a value x is equal to this: 1 over sigma times root 2 pi, we'll talk about why that crazy thing is there, times e, our friend the natural base, to the, and the rest of it is the exponent of e, okay? The negative of x minus mu, the mean, all squared. The negative does not get squared, so the numerator of that fraction is always negative, divided by 2 sigma squared. Again, mu is the mean and sigma is the standard dev. So, an example I just made up, it's probably not true at all. Let's say that for the height of adults in the United States, the average is 170 centimeters and the standard deviation is 7 centimeters. If that was the case, then the normal distribution of those heights, which is what we might expect the population to have, would be 1 over 7 root 2 pi times e to the minus x minus 170 squared all over 2 times 7 squared. Alright, so I've just shown you how to plug the mean and the standard deviation in. Let's say I want to know what the probability is that a person chosen at random from the United States, who is an adult, has a height of 170 centimeters, the mean. So I'd like you to pause the movie now and try to use your calculator to agree with my result. My coefficient out front turns out to be 0.056992. The funny thing about this particular example is that x is 170. It is the mean, and so the numerator of that exponent is 0. If the numerator of a fraction is 0, the whole fraction is 0, so we're really raising e to the 0 in this situation, which is just 1, and what we get is just that 0.57 roughly, which is surprising. The most common height, the mean, is there's a less than 6% chance that you're going to have that height. Try it again for 190 centimeters. Pause the movie and see if you can get roughly 0.1%. Not 0.1, that would be 10%, but 0.1%, 0.001. Okay, that's very, very small. And you might be wondering why even the most likely height is so unlikely. And the problem is that height is a continuous variable that can be 170.002 or 169.999. If we were to ask the question, what is the overall probability that a person's height is between 169 centimeters and 171 centimeters? That would be a much more respectable percentage. And we're going to see how to do those kind of calculations soon when we talk about z-values. So hold on for that. If you're feeling really brave, try to graph that function for the height of people in the US, the probability of finding someone with height x. I did, and after fiddling around with the window for a while and zooming in and out, I got this nice graph. You can see why they call it the bell curve. It does indeed look like a bell. It's symmetric. The top of the hill there is right at 170 centimeters, and it's symmetric going away from there. All normal or Gaussian distributions are going to have the x-axis as their horizontal asymptote. The area between the graph and the x-axis is always equal to 1. That's very weird. That blue bell-shaped part there, that has an area of 1, and I can't prove that to you without calculus, so I'm not going to try. But that is the reason why that horrible 1 over sigma times root 2 pi is out front. Using calculus, you can show that that is necessary in order to make the probability, to make the area 1. And what that signifies is that the probability of something happening is 1, right? We add up all the possible probabilities, and that corresponds to adding up that area. Something will happen, and we won't have 100%, we won't have more than 100% chance of anything happening. So that's why that horrible factor is out front. If the standard deviation is 1 and the mean is 0, we have what's called the standard normal curve. It's kind of redundant sounding, but that's what it's called. And here's the equation for that. When you make mu equal to 0, and standard deviation sigma equal to 1, the formula simplifies a lot, and it looks like that. All right, so talking about area under the curve, there's some sort of rules of thumb that are useful in working with normal distributions. If you're asking about a range of values, let's say you're asking about values ranging from one standard deviation below the mean, mu minus sigma, all the way up to one standard deviation above, mu plus sigma, that red range shown in this picture. It turns out that there's going to be a 68% chance of whatever it is that you're looking at falling between those values. That's just a standard rule of thumb for all normal distributions. If you go all the way out to 2 standard deviations below or above the mean, the light blue range there, your chances increase to 95%. So pretty certain it's going to fall in there. And 3 standard deviations, you encompass 99.7%. Alright, example 2 illustrates these rules of thumb pretty nicely. Tennis shoes apparently have an average lifetime of 450 miles, life distance, I guess, and that has a standard deviation of 50 miles. So here's a graphical depiction of that. One standard deviation above 450 would be 500, and below would be 400. That blue area has to have a total probability of 68%, and since this curve is symmetric, we can split it in half, and 34 and 34, as you can see there. But to be within 2 standard deviations of the mean has a probability of 95%. So as I'm showing here, subtracting 95 minus 68, we get 27. That must be these red pieces here. And again, because it's symmetric, each of them must be half of that, or 13.5%. All right, all probabilities added up under the curve together must be 100%. And since that leaves only 5% for these wings out here, as we call them, these green pieces. And again, since it's symmetric, each of the wings must contain 2.5% of the probability. When you break the graph up like that, answering the questions in example 2 is pretty easy. Part A asks you what's the chances that the shoes will last between 400 and 500 miles. Again, a range gives you a nice respectable answer. And it's that blue range there, 68%. Part B is asking greater than 550? Well, we'd be more than 2 standard deviations above the mean. We'd be out in the wing, and there's only a 2.5% chance of that happening. All right, we're going to do more examples and talk about something called z-values in the next part. Stay tuned.